So before I even get started, all of these slides are actually Jupyter notebooks. So if you want to look at the code, there's some additional notes also that aren't part of the slide. The link's up there. I might find my Twitter account, pretend I use it, and tweet it to IndyPy also. But yeah, so I didn't grow up in Indiana, and I found a weather data set, and I was like, oh, tornadoes, they're a thing out here. Let's play with this. So our problem, because we're doing machine learning, we need a problem to solve. So I've got a data set. I got it off of Kaggle. It's the NOAA weather data set. And it's actually only a small part of the data set because it's a really big data set, and I just wanted something quick to display. But it's got daily weather recordings from about 9,000 weather stations. So things like temperature, precipitation, fog, and of course whether or not there was a tornado. So as mentioned, our goal is just to predict, given this other weather data, if a tornado is going to form. So it's a classification problem. It's just a yes or no answer. There's not necessarily any probability of tornado, just yes, I think there will, or no, there won't. And so because Scikit-Learn is awesome, we're going to compare 4 different classifiers. So we're going to train 4 classifiers in 15-ish minutes. A couple assumptions. The data set has already been cleaned or scrubbed. There's no missing data. Everything's numbers. There's no text in there. If there's any really terrible features, we're assuming they've been removed. If you want to play with this data later, don't assume I did a good job of this. I just got it well enough that it'll run. So we have to get our data. I have it saved into a CSV file, loaded into pandas. And so our data, we can kind of look at it. What does this tell us? Maybe not much yet. But so the first thing we need to do is, so all of our data is just in this one data frame. So we need to split it out. We're going to call y is our variable where we're going to put the thing we want to predict. So that's whether or not there is a tornado funnel cloud. And then x is going to be everything else. So we just drop that one tornado column from the pandas data frame, and that's all of our features. So that's easy enough, but now we need to split our data set again. So we have all of this data together, but we need 3 different sets. We need data to train on, data to validate our classifier, and data to test on. And so essentially, it's what it sounds like. You train your model on the training data. Validation, we're going to use because we have multiple classifiers. We need something to tell us which one of them is better. And then the test set is how we do our final evaluation. So it's a really important concept. And I like to think of it, going back to school, in terms of, a human learning. So the training set's like homework. There's a lot of it. There's so much homework. You start off knowing nothing. You keep doing these exercises. You get the answers. And depending on whether you're right or wrong, you learn about the subject. So you do that a lot. Then you get to the validation. That's like your practice exam. There's fewer exercises, but if it's a good practice exam, it's not exactly anything you've seen before. So you use what you learned from your training data, from your homework, and you see how well you do on this. If you do really well, great, you're probably ready for the exam. If you don't do very well, if your score is low, you probably want to go back to that training data, to that homework, and learn some more. And then the test set's like the final exam. You see how well you did on all these examples, and that's your final score. And so everything on this chart, as you go to the left, here we go. So, the validation set can't have anything that's been seen in the training set. The test set can't have anything that's been seen in the validation or the training set. Otherwise, it's like you're cheating on your exam and, someone gave you the answers the day before. So we have to actually split our data set. We can't just talk about splitting it. So Scikit-Learn has this handy train test split. It'll split your data set into 2, so we have to do it twice. The first time we are splitting into, so we have our features, we're going to want our training and validation set kind of clumped together, and our test set. So we do that for our features, and then we also do that for our labels. We call train test split. We give it our original features and labels. Tell it we want 25% of it to be in the test data. Stratify on our labels means that we want an equal number of yes, there was a tornado in both data sets. If we train on everything that's not a tornado and then our test set is all things that are a tornado, it's not going to be a very good classifier. Random states, just useful for slides like this. Every time I want this slide, I want to get the same answers. So we've split it. We have our training and validation together and our test set. And then to get all three of our sets, we just do this one more time. We pass in our mishmash of training and validation and have it split those out. Are there any questions on training and validation before I move on quickly? All right. So now we have our training, validation, and testing data. We have our features. We have our labels. Let's talk about how we train some classifiers. We're going to look at two main types, k-nearest neighbors and support vector machines. They're two pretty common ones that you're likely to see, and they're both pretty useful. So starting with k-nearest neighbors, this is basically a majority vote. So you're going to take so we're working with weather, so if we were using this, we would take today's weather values, all those recordings, and find the ones in our training set that are the most similar to whatever today is. And then those similar ones get to vote. So here we're using k equals 3 with two classes. There's these red circles and these blue circles, and we want to know what's up with this triangle. So if you look at this plot, if we say 3 neighbors, this circle has 3 neighbors in it. 2 are red, 1 is blue, so we're going to call that triangle red. If the number of neighbors were 1, we'd only look at the one closest neighbor and we'd call it blue. So some important things that are going to affect your classifier: how many neighbors you pick. So as you see, whether you pick 1, 2, or 3 is going to depend on whether this is classified red or blue. So that's going to affect how your classifier works. The other one, it's a parameter called weights. So it just determines if the closer neighbors have a more important vote, if what they say is more important than the ones that are farther away. And so here in this example, we just did uniform. So I just counted the 3, and they are all equally voting. So that's the picture, and here's how we actually do this in code. Zoom in a little bit. So Scikit-Learn has neighbors, which is where we're going to get our classifier. And they have a metrics package where we're going to get accuracy score. That's just going to help us figure out how good our classifier is. So we say we want 15 neighbors. We want our weights to be uniform. And all we do to create this classifier is neighbors.kneighborsClassifier, pass in our 2 parameters, and this is our classifier. But we have to train it. So it has a nice fit method. We say clf.fit, give it our training features and our training labels, and that's it. We've trained a classifier. If we want to know what it predicts, it has a predict function. We give it our validation features, not the labels, just the features. And for each of those examples, it tells you what it would predict. And then, so here's where that accuracy score comes in. We call accuracy score. We give it the actual labels for the validation set and our predictions. We do some nice formatting to get into a %, and we are at almost 81% accuracy. So not bad. 81% of the time, this would tell you whether or not there would be a tornado. But let's look at some other classifiers, see how good we can do. So support vector machines, they work a little differently. Instead of doing a vote, they're trying to draw something in between the 2 classes. So here it's a line. If you have a lot of dimensions, it would be a plane, or maybe a circle around your data, just some way of separating the data out. We're also looking at 2 different parameters here. We have C is a penalty function. So when it's training this classifier, a high value is going to try really hard to get every single example right. So you're going to have, so if there was a lot of overlap between these classes, you'd have this really complex line or plane separating your data. A lower value of C is going to not penalize so harshly, and it's going to try and give you a simpler model. So which one you want is going to depend on how your classifier is doing. Is it overfitting? Is it fitting too much noise and not real information in your data set? You might want to bring C down. The other important thing about support vector machines is the thing called a kernel, and that's just the type of boundary. So this is linear, it's a line. It could be a polynomial. It could be RBF, radial basis function, which is sort of drawing circles around your data to get the lines. But it's different ways of reshaping the data and drawing those boundaries. So while it works really differently from k-nearest neighbors, when you want to use it, it's very similar. There's an SVM package. We're importing SVC, our same old accuracy score. And to get our classifier, it's very similar. We pass in our two parameters, this time to SVC. We get our support vector machine. We use the exact same fit and predict methods as we did with k-nearest neighbors, which is one of the nicest things about Scikit-Learn, is they're really good about just about everything has the same method. So everything has fit, everything that's going to try and predict something has predict. It's very consistent, which is really helpful for moving from one to the other. And then if we want to look at our accuracy using accuracy score again, this one's only got about 75% accuracy. All right, so we've got two classifiers. One is better than the other. But let's look at some more, because I promised 4 classifiers. So let's do 4 more. So we have 2 support vector machines with 2 different kernels and values of C, 2 k-nearest neighbors classifiers, different numbers of neighbors. One is uniform, one is distance-based. And so we create these 4 different classifiers, and you could do this for, in theory, any number of classifiers you wanted to do. So if you were interested in just support vector machines, you might pick a few more support vector machines. But anyway, you want to create all of your classifiers, and then you just go through the same steps for all of them. You fit all of the classifiers, giving them all your training data. And then you predict, again, with all 4 classifiers on your validation data. So you have 4 sets of predictions. And you want to, we can take the accuracy score of each one of them, validation, all the different predictions, and see which one did the best. And so here we have our second KNN with about 82%, and if we scroll back quickly, the second KNN has 10 neighbors and distance-based. So this is our best performing classifier. So we're almost done, but we can't go ahead and say, hey, I've got this classifier, and I'm going to guess about 83% of the time it'll tell you whether or not there's going to be a tornado, and it'll be right. Because remember, we have that test set of data that we haven't looked at yet. So now we have to actually evaluate our winner. So we're going to retrain it on, if you remember when we split, we had this data where the training and validation data was all kind of clumped together. So we've already looked at the training data. We can't use it in our test. Why not actually train the model on it? So you can retrain, you don't have to, but you can retrain your classifier on the training and validation data together. Do your predictions, get your accuracy, this time on the test set, passing the test set, evaluating on the test set. And then our final accuracy is almost 84%. So we've only looked at 4, maybe 6 classifiers, but if you wanted to try other methods, this is what you would do. You'd get whatever classifiers you thought might work, train them all, use the validation set to pick the best one, and then your one best one, you go on the test set. And this is your best guess at given real-world data. So like if you plug this in and live to the NOAA data set and get real weather, your best guess at how well it will perform. So you are all more than welcome to go home and try and beat my classifier. I'm pretty sure you can. That's everything. So if there's questions, I can answer either up here or afterwards.